Hi everyone, Mr. Ang here. So today in this video, we are going to go through the WA3 answers for the 2023 paper. So let's start with the MCQs. Okay, question 1 asks, which of the following points is the most likely to be the center of gravity if we have this non-uniform object balanced about a pivot? So our pivot here at the bottom is very clearly marked out, and then we have the statement here that says it is balanced. So what does something being balanced mean? Okay, there is no moment. And if there is no moment, okay, therefore there is no turning effect. So what are the forces that are acting on this body? Of course, we know that there is the weight, which comes from the center of gravity, so that the question already has told you, okay? And my other force would be the normal reaction force, because this pivot must be touching the ground somewhere. However, we know that the normal reaction force acts directly upwards, okay? And in this case over here, the pivot is the thing that's touching the ground, so it's acting from the pivot. So because of that, my normal reaction force does not have a moment because it is acting directly through the pivot. So in which case, I can very quickly erase this normal reaction force and focus on the weight, which seems to come from the center of gravity. So if the normal reaction force has no moments, the weight must therefore also have no moments. And if that's the case, this tells us that the line of action of the weight must pass through the pivot. So our answer will therefore be A, because if you draw the force, okay, vertically downwards, and you continue the line of action, you can see that it passes through the pivot, and therefore there is no moment. Okay, for the rest of the options B, C, and D, there will be a moment because it does not pass through the pivot, and therefore there will be some sort of perpendicular distance. When you multiply that by the weight of this object, that will give you a moment, a turning effect. Question 2, same thing. Okay, we have a person standing on a plank and we're trying to find the most likely perpendicular distance. So first thing, we want to draw the weight. Okay, so you see over here very clearly, I've got weight acting downwards. Now, perpendicular distance, remember that means it must be right angles to my force. So immediately I can cross out options B and D because they are parallel. They're not at right angles. Then looking at A and C, it's very clear that C is not the perpendicular distance because it is not from either of the possible pivots here and here to the force itself. And that gives us A as the only option left. And that's why A is the answer. It is the perpendicular distance from the man's weight to the pivot right at the bottom left there. 3. Which of the following is not an energy store? So this one you just have to remember. Okay, the option is C because the chemical and the elastic potential stores are both stores as well as the nuclear store. It's also good that you remember what the other 3 stores are. We've got a total of 6. So joining the 2 potential stores and option A and B, we have the gravitational potential store. And then besides the nuclear store, we also have the kinetic store and the internal store. In fact, light is not a store, but light is actually a wave. And you might recall, waves are one way of propagating or transferring energy from one store to another store or one object to another object. So while there's no light store, light is a way to transfer energy from one place to another place. Okay, question 4. The input power of an aircon is 3000 watts. And assuming that it was switched on for 2 hours, what was the total energy consumption of the air conditioner? So the first thing that we have to do is figure out what the formula is. So you might recall for power, okay, the formula is power equals to work done divided by time because power is the rate at which work is done. The next thing is we substitute in our figures in SI units. So 2 hours will be 7,200 seconds. Okay, I'll leave that to you to figure that out if you can't see immediately. And now we want to find the total energy consumption. So that's the work done, which will therefore be the power times the time. So you take 3000 multiplied by 7200. What you're actually going to get is 21.6 million. So that's 21600 and three more zeros here. Okay, so be very careful. Some of you might have picked D because the number looked right, but actually answer is A because megajoules. Okay, remember that mega means million or 10 to the power of 6. So 21.6 megajoules is 21.6 million joules, which you can see over here. Okay, that is the answer of our calculations. Question 5. A pure liquid undergoes boiling. Which of the following increases during this period? The internal energy, the internal kinetic energy, or the internal potential energy? So it's good to remember that internal energy is actually made up of the kinetic energy and the potential energy of all the particles. So when you have a pure liquid undergoing boiling, what is happening here? This is a change of states. So if I have this change of state, what that means is my particles are overcoming the attractive forces or overcoming the forces of attraction. And whatever energy you are providing to the liquid is not going into its kinetic energy. That is why when you look at the heating curve, at the change of state, the temperature remains constant. So therefore, the internal kinetic energy does not increase. Okay, it stays at the same temperature. So what that means is the potential energy is increasing because the particles in the liquid, they are overcoming the forces of attraction. But considering what I said just now, remember that internal energy is made up of the sum of kinetic and potential energy of the particles. So therefore, it is also increasing. And as you would expect, because you are boiling the liquid, you are transferring energy into it. Therefore, the internal energy must increase. So the answer is option C, 1 and 3. Now moving on to our structured questions. Okay, figure 6.1 shows the incomplete table. I've just left it here. These are statements you have to remember. Okay, so for forces, we usually say that the forces between the particles in a solid are very strong. In a liquid, they are strong. In a gas, that is the only time we'll say that they are weak. Okay, so don't go around making the mistake saying that the forces between particles in a liquid, they are weak. So similarly, the arrangement of particles, both solids and liquids, they are closely packed. Solids are very closely packed, liquids are closely packed. The difference between them is that in a solid, the particles are arranged in an orderly manner or in a regular pattern. Okay, both of these are acceptable. Then, in a liquid, they are arranged disorderly or randomly. As for the motion of particles, okay, we know that in a solid, the particles are not able to move about. However, they are still moving. And if they're still moving, what are they doing? They are vibrating about their fixed positions. In a liquid, the particles are able to move around relative to each other. So what we write is they slide past each other. Why do we say they slide past each other? Because they are still closely packed together. In a sense, they are still touching each other. So rather than, like in a gas where they're free to move, they are still forced to be in contact and they are sliding past each other. So these are kind of the key words that are good for you to remember to describe, okay, the forces, the arrangement of particles, and the motion of the particles in solids and liquids. Okay, if you want to find out about the gases, you can actually go and refer to previous videos or your notes, okay, where we spoke about that in more detail. So question 7, we have a sealed jar filled with gas. So using the concept of forces and arrangement of particles, explain why the density of a gas is generally low. So before we start trying to come up with our forces and arrangement of particles in a gas, I think the first thing that's very important is to understand what density is. Okay, remember from a previous chapter, density rho is given by the mass over the volume. So if the density of a gas is low, it tells us one of two things. Either the mass is very low or the volume is very high. Okay, so that's why the density is low. So using those things together with our forces and particles, this is our answer. Because the forces of attraction between the particles are negligible or very small, the particles are very far apart in a random arrangement. So because they're very far apart inside this jar, there are very, very few particles per unit volume. So you can see over here, actually the volume, I'm not increasing the volume. I didn't say I'm heating the volume up. So let's erase that. And this actually tells us that there is very little mass inside this jar. So that's why the density is very, very low. So in fact, average density of gases is about 1,000 times less than liquids. So the air around us, the density is roughly 1 or 2 kilograms per cubic meter. Okay, whereas for liquids in a cubic meter, it would be 1,000 liters of water, so that would be 1,000 kilograms. Okay, so it's about 1,000 times less. Okay, part B. The gas in the jar is heated slowly. So state how the pressure in the jar changes. Explain your answer. So I'm going to do the same thing again. What is the definition of pressure? Okay, pressure is the force per unit area. Now in this case over here, as I heat the jar up, is the area of the jar changing? No. So therefore, the area is constant. So for pressure to increase, okay, the force must increase. And why does the pressure increase and why does the force increase? Because as the gas is heated, the average kinetic energy of the particles increase. So when your kinetic energy goes up, it means that the velocity or the speed of each particle on average goes up. So if the particles are moving faster, what is going to happen? They are going to collide with the walls of the jar much more frequently, right? Because they are moving faster, it takes less time for them to go from one end to the other end. And because they're going faster, they are going to collide with the walls of the jar with more force, right? The faster something moves, the more force it will exert when it hits something else. So these two things combined, okay, lead to a greater amount of force and therefore a greater amount of pressure. So question 8, now we have a moments question. We have a simple version of a wheelbarrow over here. So this part here, I believe a lot of students would have missed. The wheelbarrow is uniform and it has a mass of 5 kilograms. Okay, then you've got a load of 10 kilograms resting on a wheelbarrow. So this here is 10 kg. Okay, and we have a force applied to keep it horizontal. So, what is meant by the principle of moments? This one is just a definition question. Okay, when an object is at equilibrium, the sum of the clockwise moments about one pivot is equal to the sum of the anti-clockwise moments about the same pivot. Now, on this figure, to label the pivot very clearly, we have over here the wheel, so you can label it here. Okay, alternatively, I would also accept if you label it below. Okay, both are fine. They do not change the perpendicular distances involved. Now, before I move on to the next part, okay, let us now draw the the weight of our wheelbarrow. Because it is uniform, what is that telling us? It's telling us that the center of gravity is from the middle. And therefore, okay, this weight over here must come from the middle, which, given that the wheelbarrow is 1.2 meters long, it means that the perpendicular distance to my pivot is 0.6 meters long. Now, 5 kilograms means that it must be 50 newtons because of our formula W equals to mg. Similarly, for our load, okay, over here, 10 kilograms means that it is 100 newtons. Okay, so remember this. You can pause this here, you can come back to this, okay, while I'm explaining the next part if you do need that little bit more time. So now, to calculate the minimum force needed to keep the wheelbarrow horizontal, what do we have to do? Okay, first, we must write down that the formula of the moments are force times the perpendicular distance. Next, using the principle of moments, which we put out in part A, the sum of the clockwise moments is equal to the sum of the anti-clockwise moments about my pivot over here or over here. So where are my forces again? I've got 100 newtons here, and I've got 50 newtons here, And this 50 newtons has a perpendicular distance of 0.6 meters. So where are my clockwise moments from? Where are my anti-clockwise moments from? Looking at my pivot on the left. Okay, let's consider the effect of the forces. My 50 newtons would want to turn my wheelbarrow this way. 100 newtons would want to turn it the same way. So these two are my anti-clockwise moments. As for force F, it wants to turn the wheelbarrow the other way, so that is the clockwise moment. So putting that all together, what that means is that my anti-clockwise moments over here, 100 newtons times 0.8 meters and 50 newtons times 0.6 meters, added together must be the moment due to F, which is the magnitude of F multiplied by 1.2 meters. Okay, a very common mistake that students might make is try to add up 50 and 100 newtons. Now, moments, okay, must be calculated individually. We cannot add up the distances, we cannot add up the forces. Only after you find the moments, then you can add them up together. So, doing the math, which I'm going to skip here, we get that the force is 91.7 newtons after rounding off to 3 significant figures. So for question 9, we start off with a diagram of a roller coaster. So you see over here, the cart has a mass of 450 kilograms, and it starts from A at rest, safely completes the loop of of diameter 10 meters, and comes to a stop at D. The track is smooth for the entire track except for the length, 25 meters between C and D. Now, before we start looking at the question, let's figure out what information it's giving us. Okay, besides the obvious that the mass is 450 kilograms, okay, what else is it telling us? Okay, it is telling us that it is at rest at A, which means at A, there is no kinetic energy. And also at D, it comes to a stop, also no kinetic energy there. And finally, it is telling us that it is smooth for between the whole track until C and D. So what that means is smooth, there is no friction, and friction, okay, is the main culprit when it comes to transferring energy from within a system to the surroundings. So if there's no friction, that means that energy is conserved. So between A, B, and C, they should have the same amount of total energy distributed among all the stores. But from C to D, that may change. So let's start with the first part now. For the cart to safely clear the loop, it needs a minimum speed at B given by this V minimum of equals to square root RG. Okay, this actually is a formula you could derive if you learnt about circular motion, which is a topic at JC Physics if you take it. Okay, so it's beyond our syllabus right now to derive, but if you do take physics in JC, you continue to take it, okay, you eventually learn how to derive this formula. What actually happens is if you do not meet this minimum velocity, the cart won't actually complete the loop properly, it will fall off at the top. So now getting back to the question, what I'm going to do here instead of putting in the values of R and G to find V minimum, I'm actually going to just do the algebra. We know that the formula for kinetic energy is half mv squared, and because it's half mv squared, we can put in V minimum squared, giving us Rg. So we don't need to put in values, we don't need to take the square root of anything here. Makes it much nicer. Now, another mistake which I think students might make is to forget that the radius is half a diameter and you end up putting 10 instead of 5 into the formula. But assuming you don't make that mistake, okay, you put in your correct values, you're going to end up with 11,250, which when rounded off to 3SF gives you 11,300 joules. So that's our kinetic store at B. Now for the next part, the total energy at B. We already know the kinetic store is 11,250. Now notice I use this value. Why do I use this value? Because we use the intermediate values from previous parts. If I just keep using 3SF rounded off values, eventually all these rounding errors might accumulate, okay, and make the final answer very inaccurate. So just the lesson as well, intermediate values are the values to use, okay, in your calculations. Only round off at the end when you are presenting your final answer. Okay, so that's our kinetic store. What about our gravitational potential store? The formula for that is mgh, as you well know, and substituting it gives us, okay, 45,000 joules. Are there any other stores here? Okay, you can ask yourself that question and you should come to the conclusion that no, there aren't any other stores here. So our total energy is the sum of these two. That gives us 56,250, which again rounds off to 56,300 joules. Okay, 3SF. But in our next part, we want to make sure that we use our intermediate value. And it's because of what I said earlier. The track is smooth, there is no friction, so we are allowed to use the conservation of energy. So this principle of conservation of energy tells us that the total energy of all the stores at A is equal to the total energy at B. And we already calculated in part 2 the total energy at B, 56,250 joules. Now at A, earlier I mentioned that because it is at rest, okay, EK, or the energy in the kinetic store, is 0. So that means that the rest of the energy must be in the gravitational potential store. So all of it is in mgh. Doing the math tells us that h is 12.5 meters. Okay, notice now this time I did not need to round off the 3SF. It gave me a nice exact answer. If you had used 56,300, okay, you would have gotten a slightly different answer, which you would have then needed to round off. In this case, it would have still rounded off to 12.5, okay, but not every question will be so nice. So now moving on to part B. Okay, when the cart moved from C to D, there was sound heard. And when the cart came to a stop at D, the temperature of the cart was higher than when it had first started. So to describe energy transfers from C to D. So at C, okay, you will notice that it is on the ground. So on the ground here, that tells us that our potential or gravitational potential energy is 0. And for D, it's the same thing as well. So the only energy here is in the kinetic store. Okay, so it's got some value here, 56,250 joules. And over here in the kinetic store is 0 because, like the question stated, it is at rest. Now, what energy transfers have occurred? Okay, in the kinetic store, it is transferred to the internal store because it tells us that the temperature of the cart was higher. So that means that the cart heated up, it had gained some internal energy. In addition, there was sound heard. Okay, so the sound heard means that it has been transferred out of the system by propagation of waves because sound is a wave. Okay, this extra part about heating, not necessary, but we know that, okay, if the cart is going to be at a higher temperature than the surroundings, it is going to transfer some of that energy via heating to the surroundings. Okay, in fact, in the next chapter after this, where we talk about transfer of heat, we will learn about the different ways that this occurs. And then B part 2, calculate the average frictional force exerted on the cart from C to D. So again, okay, at D, the kinetic and the gravitational potential store is 0 because it's on the ground, it's stationary. So you can see over here on the right, I've already put down EP and EK, both are 0. So what that means is that the energy transferred from the original kinetic and gravitational potential store of 56,250 joules is the work done by friction because work is the transfer of energy. And what that means is, from part A, the total energy at C is equal to the total energy at B because of conservation of energy, 56,250 joules. the work done by friction must be the force times the distance traveled in the direction of the force. So friction must have acted horizontally and the cart traveled 25 meters horizontally. Putting that all together, okay, the work done is 56,250 joules, which is the force times 25 meters. You do the math, and you will find that the force is 2,250 newtons. Okay, so that's the end of the solutions. If you need some more time, you can rewatch the parts, okay, or you can watch it at a slower speed as well.